Topic 7.2 Summary, Part 1, Mass Defect and Binding Energy. Atoms are small. Protons, neutrons, and electrons are even smaller. We need a tiny unit of mass. Meet the Unified Atomic Mass Unit, the symbol μ. The Unified Mass Unit is defined to be exactly 1/12 of the mass of an atom of carbon-12. One Unified Mass Unit is equal to 1.66054002 times 10 to the negative 27th kilograms. Mass defect and binding energy. If we look up the mass of carbon-14, it's in your book on page 526, we'll find that the mass of a carbon-14 atom is 14.003242 unified atomic mass units. Notice we need a lot of significant digits for what we're working on right now. Now find the mass of the nucleus by subtracting the mass of the electrons. Well, the mass of an electron is 0.0005486 atomic mass units, so multiply that by 6 and subtract it from the mass of the carbon-14 atom, and we get 13.9999504 atomic mass units. So all we did is we looked up the mass of a carbon-14 atom, and we looked up the mass of an electron, and subtracted the mass of 6 electrons from the carbon-14 atom, which ought to give us the mass of the carbon-14 nucleus. So at the top of the page, we're just recapping what we had at the bottom of the previous slide. We looked up the mass of a carbon-14 atom, we subtracted the mass of 6 electrons, and determined that the mass of a carbon-14 nucleus is 13.9999504 atomic mass units. Now we're going to find the total mass of 6 protons and 8 neutrons, because that's what the carbon-14 nucleus is made of. So if we take the mass of a proton and multiply by 6, plus the mass of a neutron and multiply by 8, and add that up, we get 14.112976 atomic mass units. Whoa, we have a problem. Where's the missing mass? So again, what we see here is that the mass of the individual particles that make up a carbon-14 nucleus is greater than the mass of a carbon-14 nucleus. We seem to have something that's violating the law of conservation of mass. So if we actually want to figure out how much mass we're missing, we take the top line there, which again is the 14.112976 atomic mass units. That's the sum of the protons and the neutrons in the nucleus, and subtract that from that the mass of the actual nucleus, and we get a difference of 0.1130256 atomic mass units. This is called the mass defect, which is probably a corruption of mass deficit. It's the missing mass, but it's called the mass defect. The mass defect of the nucleus has been converted into energy, and it's stored in the nucleus as a form of potential energy. The energy is called binding energy, the binding energy of the nucleus. I'm sure you're familiar with Einstein's mass energy formula, E = mc squared. Well, now we actually get to use it. We can use E = mc squared to calculate the energy that's stored in the nucleus. The mass defect is 0.1130256 atomic mass units. We can use the conversion from the previous slide to convert that to kilograms, and then we could solve for the energy in joules, and then convert it to electron volts. But if we do all that stuff, we'll discover that one atomic mass unit converts to 931.5 mega electron volts. That's a conversion factor that's in your data booklet, but it's one that you should probably memorize. Again, one atomic mass unit, when it gets converted to energy using E = mc squared, gives an energy of 931.5 mega electron volts. So if we multiply the mass defect from our problem we're working on, 0.1130256 atomic mass units, times 931.5 mega electron volts per atomic mass unit, we find out that the energy stored in the nucleus, the binding energy, is 105.3 MeVs, or 105.3 mega electron volts. This is a graph you should be familiar with. It's called a binding energy curve. And the way this graph is created is if you look on the y-axis, they've taken the average binding energy per nucleon for all the different elements. So they take the binding energy of the nucleus for a particular element and divide that by how many nucleons that element has, and you get this graph. And what it tells you, it turns out, is that the most stable element is iron. You see it here in the middle, iron 56. And if we go off in either direction, things become less stable. If we go off to the right, we get larger and larger and larger nuclei, which are easier and easier to split. And when we get way over to the right-hand side, we have nuclei that are unstable and tend to be radioactive. On the left-hand side of this chart, we actually have the nuclei that, under the right conditions, can be forced to fuse together. Nuclear fusion is something we'll talk about later on. Okay, that's all. We'll see you next time. Except I do have a wacky word of the week for you. Counterfeiter. Counterfeiter, a worker who puts together kitchen cabinets.